The next thing I want to talk about is this notion, which is called convolution, which is quite a fundamental notion in Fourier analysis. And it comes up a lot if you use Fourier analysis to prove things in additive combinatorics, which is something I think we'll see maybe sometimes in this program, considering the new breakthrough on the 3 times arithmetic progression stuff. Okay, so what is the convolution? If I have 2 functions, it's an operator, binary operator. So if I have 2 functions on my group, I'll define their convolution, which is another function that goes from G to C. And it's defined as the following. So it maps X to expected value Y in G of X minus Y, G of Y. And you can do a change of variable, and you can write this also as expected value over Z. So if we call this thing Z, so it becomes f of Z, G of X minus Z. So because of that, it's commutative. Doesn't matter, the order doesn't matter. Okay, and why is it useful for us, at least in this kind of discrete applications? One nice thing about it is that you can do things like that. So let's say my group is, say, Z2 to the n, and I have a function f here. The n, say to r. And now, suppose I want to, for every point x, I want to average the function over, say, Hamming ball of radius r around x. So this is, say, r, so Hamming ball. So I want x to be mapped to average of, let's say, f of y, where y selected this Hamming ball of radius r around the point x. Okay, something like that. And you can easily represent these kind of things with convolution and study them that way. So y. So generally, let's say let A be a subset of G. And suppose I want to look at the function that maps X to this thing, that you select a point from the set A at random, and then you look at the f of X plus Y, or let's say minus Y to be nicer with convolution. Right, so if I take A to be, say, now the Hamming ball of radius r around 0, I'm going to get this thing that I want, because it's going to be x minus something that's chosen from that Hamming ball. So it's going to be around point x, right? So I'm just changing the center. So, so how do I represent this with convolution? I can define this thing mu of A. So this maps every point y to there's this normalization factor, G size of A, and then whether the point is Y. So this is the indicator function of the set A. It is 1 if Y is in A and 0 otherwise. Now with this notation, I can now write this function G. So now G is really just going to be F convolved with this mu A. So this is something that one does a lot in additive combinatorics. For example, yeah, when you want to average over another set, you define these measures, and you can write it in this convolution form. Now, okay, so that's, yeah, like one way that it comes up in applications, at least for us. And now convolution has some really nice property, like with respect to the Fourier transform. let's start this, write this as a proposition that if I have two function f, then the Fourier transform of their convolution is just the product of the two the two transforms, the pointwise product. So if you know what the Fourier transform of f is and what the Fourier transform of g is, then you can immediately get the Fourier transform of f convolve g. So it has this nice property. Let's prove this. It's pretty easy. So it's at some character chi. What is this thing? By definition, this is the, so let's write expected value of x. Now the convolution is expected value of y, f of x minus y, g of y. So this is just the convolution at point x. And now I have to multiply this, take the inner product of this with my character, so chi bar on x, right? So that's just the definition of the Fourier coefficient. I'm taking the inner product of my function, which is this convolution, with the character. Okay, so now we can just plug in the Fourier coefficients and expand this thing. Going to be expected value of x. Let's put all the expected values out. And then I'm going to have a sum for this one and a sum for the sum, let's say, the characters of this one. Characters and y, and then finally I can group these things. So for y, I'm going to have phi y. So this minus y and this y. And for x, I'm going to have okay, so that's just everything is equality, right? Equality is always trivial. Just expand it and group these characters together. Now I have these two expected values which disappeared. Keep those expected value of x and y. Now, because I'm taking these expected values, these gonna be 0 unless these are principal characters, right? So when I'm averaging over y, the only way I'm gonna get non-zero is if this is the principal character. And the only way I'm going to get a non-zero thing here is if this is the principal characters. So this is the only case, the only surviving terms are going to be phi being the same as psi being the same as chi. If this is not the case, this term is going to disappear when you take the expected value. So these are the only surviving terms. In that case, I'm going to have, so the whole sum is going to be now sum over, let's say, I mean, there's no sum anymore, right? It's just chi, because both of these have to be equal. So that's going to be, just write this here. Right, this is clear. Okay, let me now also define something that's going to come up more in the later talks, which is the noise operator using convolution. So here we saw that we're averaging over this Hamming ball around X, but you can also average over distributions. You can pick X, then modify it randomly, and then average with respect to that. And one natural way is to add coordinate-wise noise. So let's say my function is, so back to the cube, z2 to the n, let's say r or c, better. And now let's say I want to just modify each coordinate with some probability independently. So to do that, let's pick a parameter. So delta is some number in the interval 0, 1. And let me define a distribution, probability distribution here. Mu delta be the distribution on v2 to the n, defined as follows. I'm going to tell you how to sample according to delta, which is so the probability that xi is going to be 1 is set it to be 1 minus delta over 2, and probability that xi is 0 is going to be 1 plus delta over 2, and this is independently. So for each coordinate, I'll independently sample it to be 1 or 0 with these probabilities, 1 minus delta over 2, and 0 with probability 1 plus delta over 2. So that gives me a distribution over z2 to the n, which I denoted by mu delta. So now let's look at this operator, which we call this noise operator, T delta. So this takes a function f and averages it with this noise. So it's gonna T delta of f, it's gonna map any point x to its expected value of y, f of x plus y, where y is sampled from this mu delta. So what is happening here? What is x plus delta, x plus y? Sorry. So let's call this z. So what happens here is that the probability that zi is the same as xi is when this one is selected to be 0. So that's going to be 1 plus delta over 2. And the probability that this is corrupted, so zi is different from xi, it's going to be 1 minus delta over 2, right? So it's adding noise to this point x and averaging over this noise. So right, maybe better to use y here to be consistent. Okay, yeah, so here's what we're doing. We pick for any point x, we're kind of averaging x with this noise. So over randomly modifying it and averaging. Yeah.
So here in the notation, like delta equals 0 corresponds to pure noise.
Exactly. So delta equals 0 is, yeah, like pure noise. So if delta is 0, then basically we lose our point x, right? So this y is going to be with probability half 1, with probability half 0. So like it doesn't matter what x is, it's just going to be the average of f. So yeah, I wanted to actually, it's the next thing I wanted to say, is the two cases of delta equals to 0 and delta equals to 1. Okay, maybe start with delta equals 1. This is no noise. T delta of f in this case is just f, right? So if delta is 1, I'm always 0, right? The probability that I'm 1 is going to be 0, so I'm always 0. So I'm really not changing anything. This expectation becomes exactly f of x, because y is just going to be always all 0 vector. So this is really just doesn't change anything. And when delta is 0, then you get like pure noise. And in this case, T delta of f is just going to be the, so this is just going to be the uniform distribution now. So x will be completely lost. So this will be just the average of it. So this is going to be the constant function, which just maps x, every x to the same number, which is just the expected value of f. So you get a constant. So you lose all those higher frequencies. What is left is only the base, the expected value of f. Okay, so I mean, it is a very natural thing, right? Like this definition, you just add noise and you average it. So how does this behave with respect to Fourier expansion? So this mu that we defined has a really nice Fourier expansion. So mu delta hat of s, it's pretty easy because coordinate-wise you can do the calculation, and you'll see that this is really just delta to the size of s. Okay, so the Fourier expansion of this function mu that we defined is very straightforward. It's just delta to the size of s. Now, then what is when you add noise to your, when you do this noise operator in your function, what do you get in terms of the Fourier expansion, right? So this is just a convolution of f with respect to this mu delta. And we know when you convolve, you're just multiplying the Fourier coefficients. So you're gonna get a really nice formula, which is just the sum over s delta to the size of s, f hat of s, chi s. So what happened here is when you add this noise, it kind of dampens the higher frequencies. So the larger, so let's say delta is say 1/3 or something. The higher values of s get a smaller coefficient. So it kind of starts to kill higher frequencies and just keep the lower ones, right? The extreme case when delta was 0, it kills all the Fourier coefficients except the principal one. That's why we just got, so this is, I should have mentioned it probably somewhere, that expected value of f is always, use a different color to write this. So the principal Fourier coefficient, so f hat of 0 for any group, this is just the expected value of f. So the average of f is captured by just one Fourier coefficient. And here you see when delta is 0, all the Fourier coefficients become 0 except that one. So we only keep the basic part of f. And this is kind of a spectrum thing. Now, for other values of delta, let's say when delta is 1/3, you kind of keep lower ones, and then the higher ones become smaller and smaller because you're multiplying this thing that exponentially grows, so delta to the size of s. Yeah, so that's one way of dealing with higher frequencies, often applying this noise. And it has some nice properties like hypercontractility, which will come up in the later talks. Okay, so now I want to move to applications. And I think in the context of theoretical computer science, really the first application everyone talks about is linearity testing. And I'll do the same here. So this is a problem in property testing, and here's the problem. I'm giving you a function which is from z2 to the n, z2, and I want you to tell me whether this is a linear function or far from being linear. So case one is f is linear, meaning that f of x plus y is the same as f of x plus f of y. This is mod 2, right? In the range now is in z2. So that's case one. Case two is f is epsilon far from being linear. And what does this mean? It means that for every linear g, what we want is that when f is doesn't match g on many points. Okay, so this epsilon is some parameter, just strictly larger than 0. Of course, if you want to just tell the difference between linear and nonlinear, we really have to look at the point on every point, the function on every point, because you can take a linear function and just modify it on one point, and then it won't be linear. So that's not an interesting task, because it's just you have to look at it every point. But here it's an easier task, because it's kind of a promise problem, right? Either the function is linear or far from linear, or at least we don't care if it's close. You can make a mistake. We don't care about that. So it doesn't match on many points. So yeah, so this is the problem. And there's a natural test for it, which will come. As with any property testing problem, usually the tests are very easy. And analyzing them is the hard part. Okay, so let's relate this first of all, like before actually giving you the test, to what we've been doing before. So let me define this other function now. So here the range is z2, but we've been doing functions where the range is complex numbers or real numbers. So I'm going to define this other function f, which is f of x is -1 to f of x. This is now from z2 to the n. -1 and 1. Okay, I'm just defining it this way. Now, what does being linear mean now? So if f is linear, what do I know about f of x plus y? It's going to be -1 to the f of x plus f of y, which I can write it now as -1 to the f of, let me write this actually. Which is -1 of x y, which is just f of x times f of y. Okay, so linearity translates to something we've been looking at, which is being a multiplicative function, being a character. So f is linear if and only if this capital F is a character. So our problem now is really, when we think about this capital F, we want to know whether it is a character or it's far from being a character. It has some distance from every character. So it looks already something that falls into what we've been looking at. Okay, so let's look at the natural thing we would do. So this is the test we're going to perform. Pick x and y random and independently, uniformly. And so we pick 2 points, do the natural thing. So if f of x plus y is f of x, f of y, then accept this function as being a character, else reject. Okay, so say it's not a character, or it's far from being a character. Okay, so that's our test, and it's really the most natural thing you can imagine to do. So now let's look at the cases we have. So case one, suppose this f is a character, which is the meaning that the small f is linear. So in this case, we're not going to make a mistake, right? If f is actually a character, f of x plus y is going to be f of x times of f of y. So we're going to always accept. So no error, no mistake here. I'm going to correctly accept it with probability 1. So we are good in this case. It's a one-sided error situation. Now, case 2 is the more interesting case. So in this case, we have this distance thing. So we know we're not a character, but we're actually far from being a character. So in this case, we know is that the probability that f of x is the same as chi of x is at least epsilon, and this is for every character chi. Now let's see what does this tell us about the Fourier expansion of f. So let's write this. What is this probability? F of x. So these are one and plus one minus one valued functions. So I can write this probability as this expectation. 1 minus expected value of f of x over 2. Right? Because when they are equal, I'm going to get a 1 here. And when they are not equal, I'm going to get a negative 1. And so if you look at, so it's going to be the probability that they're equal minus the probability that they're not equal here. And you get this, you have to do this 1 minus this divided by 2 to get the exact probability. Okay. So, but what is this thing? This is just the Fourier coefficient corresponding to chi, right? This is the inner product of f and chi. So this 1 minus f hat of divided by 2. Okay. So what we get is that for every character chi, this thing is at least epsilon. So it translates to this, right? So if you put this is at least epsilon, you move things around, so you get that f hat of chi is at least, so this thing being epsilon is 2 epsilon moved to the other side, you get 1 minus 2 epsilon and f hat of chi. So none of the Fourier coefficients are too close to 1. What is the linear case, by the way? So in the linear case, this itself was a character. So f was chi, some chi, right? So in that case, you have one Fourier coefficient, which is 1. Every other Fourier coefficient is 0. So we are trying to distinguish between these two cases. One is that you have like all the Fourier masses on one coefficient, which is 1. The other case is that all of them are kind of bounded away from 1, so which is this case. Okay, so that's what we know in this case too. But how does that translate to our test? Okay, so if you look at our test now, the probability that the test accepts, also we can write it as 1 plus expected value of f of x plus y, f of x of y divided by 2. Again, something similar, right? Like if these two things are equal, you get a 1 here. If they're not equal, you get a -1. So, so if you look at the probability, you get this formula for it. But this we can write as 1 plus. So you have this convolution here. Plus and minus are the same over z2 to the n. So I can just write that as f convolve f multiplied by f divided by 2. And that gives me okay. So the probability of accept has a nice formula with respect to Fourier coefficients. I can just read it off from the Fourier coefficient. And I want to say in this case, that's not too close to 1. So I have some positive chance of detecting this. And how do you deal with something like this? So we saw that the L2 norm behaves pretty nice with Fourier coefficients, right? So you can go from physical space to the Fourier space. But here I have an L3 norm. It's the sum to the cube. So I can't just say put f of x cube here, right? I don't have Parseval for power 3. But yeah, so this is pretty common that you extract the L2 part of this. So I can upper bound this by 1 plus. So how large can this be if I fix the L2 part? So this is going to be maximum I f hat of I times the L2 part. Divided by 2. Okay, so this is a pretty common trick when you're dealing with Fourier coefficients. If you want to bound things, you pull out enough maximum so that what's left there is the L2 part. Now the L2 part is, so this is now you can do Parseval there. So this is actually 1 plus I times. So this is expected value of x squared, whole thing divided by 2. Now f is taking only 1s and -1s. So this term is actually 1. This whole sum is just 1. So I can just drop that from there. Continue here. It's not blocked. So that's equal to 1 plus max. Right, so this L2 one was 1, so this I can just remove this and left with the max. But I know this maximum is at most 1 minus 2 epsilon. So I can just plug in that there. So this is at most 1 plus 1 minus 2 epsilon over 2. So that's the 1 minus epsilon. Okay, so if your function is far away from being linear, the probability that we are going to accept is going to be at most 1 minus epsilon. Can't be too close to 1. Okay, so there were two cases, right? In case 1, we won't make a mistake. If it's actually linear, we're going to accept it. In case 2, if it's far from linear, the probability that we're going to make a mistake is also bounded away from 1. And because it's one-sided, you can repeat this, right? So if you're not happy with 1 minus epsilon, you can repeat the test say log 1 over epsilon times, and you're going to improve it to a constant. So you can make it as small as you want. Right? Yeah, so it's very simple. It's a good like first example of application of these things to theoretical computer science. Yeah, and I mean the whole, like, we haven't used really anything other than the fact that characters are orthogonal, right? It's really the whole proof is just writing things in terms of Fourier coefficients and using the orthogonality, and things cancel. Okay. Questions about this? Right. Okay, so something that came up here in this proof, you see, we kind of like factored out this maximum Fourier coefficient. And like when you were dealing with this kind of expectation, this maximum Fourier coefficient kind of, we could use it to bound it, make it small. So this leads to this notion of pseudo-randomness, which again comes up a lot in, I mean, there's all these PRG studies in theoretical computer science. Also in additive combinatorics, when you study sets, you often divide between sets that look random and the sets that are structured. Okay, so let me define this, be more clear what I'm talking about. So f, let's call f, which is say function from to the n. Actually, this is for, we'll do it for general green groups. Epsilon pseudo-random if all the non-principal Fourier coefficients of it are small. So f hat of chi is less than epsilon for all non-principal Fourier coefficients. The principal one is just the average of f. So in this case, we'll forgive that one. If f is a dense set and the average, its expected value is large, it's fine. We really care about non-principal Fourier coefficients here, right? So when you write the Fourier expansion of f, you have the first term, the principal one is just the expected value of f, and the rest are these Fourier coefficients. And we want all of those other Fourier coefficients to be small. So I want to show you something that looks very similar to this proof, but it's about, say, three-term arithmetic progressions. Let's say I have a set. I don't know, let's do CP, for example, but I can do any group G such that the expected value or size of A times the size of the group P, and my function, the indicator function of this is epsilon Okay, so this is my setting. I have a subset of ZP, and it looks kind of random according to this definition. So all the Fourier coefficients of the indicator function are small. So again, one of A, this notation I'm using, just maps X to 1 if x is in A, 0 if x is not. The notation. I'm interested in counting the number of, say, 3-term arithmetic progressions in A. So let's look at that. And I'll count it in a normalized way. So what I'm going to do is I'll pick a random x for my starting point and the length of the step, a random y. And I'll look at what is the probability that x is in A, x plus y is in A, and x plus 2y is in A, right? So this is a 3-term arithmetic progression that's fully in A. Its starting point is in A, its next point is in A, and its last point is in A. So let's write this and see what we can say about this using this Fourier expansion. Okay, so what we do in these situations, we just replace our function with this Fourier expansion, right? So what you're gonna get now is expected value of x, expected value of y, and I have 3 copies of my function, and for each one I'm plugging in its Fourier expansion. So I'm gonna have these 3 sums here. So the sum chi Okay, I have this, just replace each copy of this 1A with its Fourier expansion. And now I can just distribute these sums. So I'm gonna get here is sum over chi phi y. Now this is chi of x. Okay, so yeah. Now again, very similar to what we had before. We have to look at these terms, these expected values for different characters of like triples of characters, psi, phi, chi, psi, and phi. So when is that? Let's try to understand that expected value. So I can again use the fact that these are characters and regroup them. So this, just this part equals to expected value of x and y. Then I'm gonna get phi, all of them at point x, and then times so again, so this thing, when is it not 0? So I'm gonna have maybe, yeah, I've been would have been easier if I used the index notation, but I guess it's fine. So I have these two characters here, this one and this one. So again, this expected value is 0. The only surviving term, so the only so I'm going to have that this is phi conjugate to make this the principal character. And once I have that, I'll plug that here. So, and the other case, which is chi psi phi, which if I plug that here, I'm going to have 0, which means same. Okay, so I mean, these are just two characters, and I need both of them to be 0 because I'm averaging over x and y. If they're not 0, this whole expectation is going to be 0. And this one tells me that psi and phi are related. Like if I know what phi is, I'm going to know what psi is. And if I plug into that one here, I'm going to also know that chi and phi are also supposed to be the same. So yeah, so now I can write this whole sum as sum over, let's say, let's write over phi. It's going to be phi. This one is phi. So instead of this triple sum, I ended up with just sum over one character because it's one of them has to determine the other ones, otherwise they all disappear. Okay, so this average, which kind of counts the number of three-term arithmetic progressions, it also counts the boring ones, right? Y could be 0 here, which is x repeated several times. It has a nice formula in terms of the Fourier coefficients. I can write it this way. Now, what do I know about my function? I know that it's epsilon pseudorandom. So I know that when this thing is non-zero, these are small. And the 0 case, it's just the density of the set. It's the expected value of 1a. So I'm going to separate that. So this is going to be the first case where phi is 0. So that's just alpha cube plus the case where phi is not the 0 character. Yeah, I just separated one term where this phi was the 0 principal character. So that gives me alpha cube. And then the rest is just the other characters. Now, what can I say about this sum? How do I bound it, its magnitude, using this pseudo-randomness?
Found the last term by epsilon and then use control.
Exactly. So again, we can do the same thing we did here. So just pull out, say, the last term, which is at most epsilon, and then the rest is just the sum. So this expected value that we were interested, x and y, right? how far can it be from alpha cube? So that's this term. And that I can bound by maximum over, say, r times the sum. And so this we know from the pseudo-randomness property, we know this thing is at most epsilon, right? So we have a bound like using this definition of epsilon, this thing. So that is at most epsilon times this thing is, I write this as expected value of 1 over a squared minus. So I would remove the 0 case, which is just the average of this thing. Like, I mean, what I want to say, you can bound this more in terms of, say, alpha, but just epsilon is good enough for us. Okay. So what does this show us? It shows that if the set is kind of random looking, then the number of three-term arithmetic progression kind of corresponds, it's close to what you see for a random set, right? If A was a completely random set of density alpha, then this expectation would be around alpha cube, and you get this thing too. Okay. So 5 minutes, what can I say? Yeah. So one thing, so the large Fourier coefficients are important, as you can see it here, right? Like they control some stuff, and if all of those Fourier coefficients are small, then we get the set behaves in a random way. And one important thing that comes up is to understand where these large Fourier coefficients can be. So for that, we can define this notion, which is spectral epsilon of f. So this is the set of all chi such that these I'll define it with this function, say from okay, so these are the large Fourier coefficients. So you look at where they are. So those characters where f hat chi is larger than this, because we're doing z2 to the n. Let me actually use the chi-s notation. Now, how large can this set be? So that's like the first question. Let us ask this. By Parseval, I know sum of all the squares of the Fourier coefficients. This is just the expected value of f squared. But this is because f is Boolean. This is the same as expected value of f, which is, let's denote this by alpha. So the whole sum is at least alpha. But now let's see how much these large ones contribute here. On the other hand, I can lower bound this thing, right? So sum of f hat of s squared. This is at least the size of this set times. Now, each one of these characters that are here, they're contributing at least epsilon alpha square to this sum. right? Because they're at least epsilon alpha, so you square them, contribute this much. So what we get is that at most alpha divided by times alpha. Okay, so you can't have too many of these large Fourier coefficients in this sense. They're at most 1 over alpha epsilon squared. Yeah, but I mean, the next thing I wanted to say, but I don't have time really to prove it, is so this is a very useful lemma that comes up in a lot of applications, which says this set is not, even though it can be that large, it can be an arbitrary set. So you're going to have some structure in this set. This is called Chang's lemma. Says the dimension of, if you take this set, I mean, we are in the dual group, which is also Z2 to the n. So you can look at the linear span of this set. This is at most log of 1 over times epsilon squared. So even though the size of the set is related in terms of alpha, it's like 1 over alpha, but in terms of dimension, it lives in a lower dimension space. So it's the dependency you're going to get is log. So I don't have time to prove this. That's the reason I plan for this, is that you can prove this directly using concentration of measures. It's kind of simple proof, but you can also prove it with hypercontractivity. So that would be also a good application of hypercontractivity for later. But yeah, I think I'll just stop here. So this is a use, like it comes up a lot in applications additive combinatorics, because you often have to deal with these large Fourier coefficients, and it tells you that they live in this low dimensional space. So you can extract them. You can pick that low dimensional space and get some structure about your set using that. Okay, so that's all I had planned for the lectures, but if you have questions.
Trying to get a sense for what parameters you can use this for. So, like, could you use this to try and understand, like, could you use it to understand the epsilon bias set? Like, let's say you knew all of them were pretty small, but then maybe you wanted to know, well, okay, well, which ones are at least like epsilon over 2 or something. Something like that, or what parameter regimes is the most meaningful in?
So I haven't really seen it in that's applied in like to understand pseudo-random sets, but it's more, the applications are more in additive combinatorics when you have the set A and you know, say the count of, say, some linear structure in it is up, and you want to get some subspace where the set, like do some density increment or something. And when you want to bound the dimension of that subspace, you look at these Fourier coefficients and you kind of find where they disappear. So you find the subspace according to that. So you get dependencies that are logarithmic to the density of your set. That's where it's often applied.
Wait, so the T rules that you had, the T delta,
yeah.
So is it the same thing as with the semi-group, the into the LT?
Exactly. Yeah. So yeah, you get the so these noise operators, they form a semi-group. So you can, but your delta you have to define it as an e to the minus t. If you want to define that. Any other? Yeah.
Just what's the difference between the size of the spectrum and the dimension of the span? Aren't
Well, they could.
or thought?
Yeah. They. So. Right. So these are you look at the characters as. So they live in a group, right? And the group is isomorphic to z to the n. So you look at them as elements of this group, not so yeah. So it's like really a subset of z to the n, and you look at the linear span, not over reals.
Okay, so if there are no further questions, let's then come again. We have ST, but this will be at 2 p.m. sharp.